Hi everyone, welcome back to Math 18A, College Algebra. Today is actually going to be the last lecture. I know last time I said that we'd have two more lectures, but sections 5.1 and 5.2 are very similar, so I'm just going to combine them and then we can spend more time reviewing for the final. I will be in office hours this week and probably the next week too. I'll just do the final problems from the past final exams that I posted. So that's the plan for this coming week and the following week. But yeah, I just want to say thank you guys for sticking with me throughout the semester. I know it was less than ideal, but I couldn't have asked for a better class, so thanks everyone. Let's get into the last lecture. Alrighty, so in these last couple sections we're going to be learning how to solve systems of equations. So systems of equations, we're going to be studying just two equations. You can have more than that, but we're only going to be doing two equations in a system. So you'll have two equations like ax plus by equals c, dx plus dy equals f, where your x and y are the variables, and a, b, c, d, e, f are all constants. And our goal is to solve the system for x and y. So we're going to be learning a couple different methods of doing that. So the first method we'll learn is the method of substitution, which is 5.1 in your textbook. Here are the steps to do this. So first we're going to want to solve one of the equations for one variable, so either x or y, and it'll be in terms of the other variable. Then we're going to substitute that expression that we just found in step 1 into the other equation that we haven't worked with yet. Then we're going to solve this equation in step 2 that we've created by using what we found in step 1. For whatever variable we have in that equation, we'll solve for that variable. And then we're going to back substitute. So once we've found a value of one of the variables, we just plug back in to find the value of the other variable. And then finally, we'll check our work to make sure we did everything correctly. All right, and so in this class, we're actually going to be working with linear equations for the most part in our systems. I don't know if we'll actually see any of the nonlinear ones. So let me remind you quickly of something we did a long time ago at the beginning of the semester when we worked with linear equations. Since we're solving a system of two equations, we're essentially seeing where these equations intersect. And so since they're linear, we could have like line 1 like this, line 2 like this. And so you'll notice that they have one intersection point. So you can have one solution. But let's suppose we have something, oops, that is not a line. Go back to my line tool, this one. And this one, let's say that they're parallel. Well, see, these are actually never going to intersect, right? So we can also have no solution. And finally, we can have a line like this. And let's say our second line is actually just the same exact line. Then that means that we have infinitely many solutions. Whoops, I keep doing that. Infinitely many solutions. So these are sort of the cases that you will probably run into. Alright, so now let's go ahead and do an example from one of the past finals. As always, we're going to find all possible solutions to the following system. 3x plus 5y equals 7, and 2x minus y equals 5. And so since we've only learned substitution so far, we're going to use substitution. So let's go back to our steps. We're first going to want to solve one equation for one variable in terms of the other one. So looking at this, you will tend to want to choose the equation that has like a coefficient of 1, if you can find one. So here we have a -1 technically for our coefficient on y, but it should be easier to solve for because I won't be dividing by anything. So yeah, like let's say strategize. to choose easiest variable to solve for. So yeah, coefficients of 1 are nice. So let's go ahead and solve the second equation for y. Alright, so that'll be our first step. 2x minus y equals 5. So why don't we take our 2x to the other side, minus 2x. I have negative y equals negative 2x plus 5. I'll write the negative 2x first. It doesn't matter. You can just write it as 5 minus 2x as well. That would be fine. I just tend to like to keep it like this. So it's in the y equals mx plus b form. And then the last part here, we'll want to divide by negative 1. Right, so I can get 1y rather than negative 1y. And we'll take it over here. Y equals, changing the sign on everything, that's 2x minus 5. Alright, so step 1 done. Let's go ahead and look at what step 2 is. We're going to substitute the expression found in step 1 into the other equation. So we're going to take this and put it in the first equation, the one that we haven't touched yet. So step 2, take y equals 2x minus 5, what we just solved for. Make sure I did that correctly, yeah. And plug into first equation. And so let me rewrite the first equation also. We have 3x plus 5y equals 7. Right. Okay, so we've solved for y. So instead of y, I'm going to plug in something that is equivalent to y. So instead of y, I'm going to plug in 2x minus 5, leaving everything else the same. We're only switching out the y here. Alright, and I believe that's all we had to do for step 2. So first we're just substituting. Then in step 3, we're going to want to solve this equation for the variable that we have in this equation. So here we only have x, the x variable now. So we're going to want to solve this equation for x. So that's kind of how this whole strategy works, is to get rid of one of the variables first so that I can solve for the other one, and then we can go back and figure out what the other variable is. So we have 3x plus 5 times 2x minus 5 equals 7. Let's go ahead and distribute this 5. 3x plus 10x minus 25 equals 7. We will combine our like terms. Maybe I should annotate while I'm doing this too. Distribute. Combine like terms. We haven't really done this in a while. Combine like terms. And so my x's, I have 13x. And then I need to combine the constant terms. So to do that, I will add the 25 to both sides to get it to cancel on this left-hand side and end up with 7 plus 25, that should be 32, right? And then finally, we just have to divide by this 13 so that x equals 32 over 13. And that's really disgusting, but I believe we did everything correctly. I'll go back and check. Well, it looks like I did everything correctly, so we'll go ahead and continue, and we'll check our work at the end to make sure everything went correctly, but it's looking like we are doing it right. So let's go do step 4. Back substitute the value found in step 3 to solve for the other variable. Alright, so we know what x is now. We have part of our solution. But we're going to want to solve for y also. So let's go and solve for y. So we just have to take one of our original equations and plug our x value in that we solved for. So I will probably choose to take the second equation. It looks a little bit nicer. I won't have to do as much multiplication. So let's go ahead and I'll write that down too. Strategize to use the simpler equation to solve for the other variable. And you don't have to choose the easier one, but it makes sense to. You should get the same answer if you choose the other one, but I just don't like to do that much multiplication if I can avoid it. So let's go ahead and choose the second equation. 2x minus y equals 5. Double check that. Yes, 2x minus y equals 5. And then our value x equals 32 over 13. Alright, so we're going to want to plug this in for x, and then you'll see that we only have y left in this equation. So then we can solve for y. Alright, so plug in x. So 2 times 32 over 13 minus y equals 5. Alright, so we have this 2 times a fraction. The denominator doesn't have a factor of 2, so I can't reduce this at all. So I'm just going to have to multiply straight through. And remember, you multiply the top together because this is 2 over 1. So I will have 64, 2 times 32 is 64, over 13 minus y equals 5. So now I have to solve for y. So what I'm going to want to do is take this 64 over 13 to the other side, I guess. So subtract it from both sides. Cancels out here. I'm left with negative y equals 5 minus 64 over 13. So in order to solve this, we need to get a common denominator. So need common denominator. So keep in mind that this 5 is just 5 over 1. So the common denominator that I'm going to go for is just 13. So I need to multiply this 5 over 1 by 13 over 13. So multiply 5 over 1 by 13 over 13. Because then you'll see that we get this 13 in the denominator, and then we'll be able to combine the numerators. So 5 times 13, let's see, 5 times 12 is 60, so that should give me 65 over 13 minus 64 over 13. So that actually worked out kind of nicely. If I do the subtraction, you'll find that you get 1 over 13. Let me go to another page. So I end up with negative y equals 65 minus 64. That's going to give me that 1 over 13. And then finally, I don't want negative y, I just want y. So we're going to divide both sides by negative 1. Negative 1 just changes the sign of everything, so y is going to be negative 1/13. So we've now solved for both x and y. You can write your answer as an ordered pair, or just as like x equals whatever, y equals whatever. What was x? It was 32 over 13. So 32 over 13. Y equals negative 1 over 13. You could write it like this. You could also write it as the ordered pair. 32 over 13, negative 1 over 13, because remember we're solving for where these two lines intersect, so you can write it as a point on the graph, and that would be fine. So yeah, take either of these. They're the same thing. But let's actually check our work to make sure that we did this correctly. So let's go ahead and do step 5, check. So let me go back and copy our equations that we had. 3x plus 5y equals 7. And 2x minus y equals 5. It's always a good idea to check, but keep in mind if you're running out of time, then I would skip this step probably, but yeah, you know, if you got time, it's a good idea to go back and check to make sure you did it correctly. So we have our solution is x equals 32 over 13, and y equals negative 1 over 13. I believe, let me double check that, yes, okay. So to check, all we have to do is plug these in to both equations, because it has to satisfy both of these equations. So we'll do the first equation. 3 times x, which is 32 over 13. At least they're both over 13, so we can already add them together. Plus 5 times y, which is negative 1 over 13. And we want to verify that this equals 7. So we're checking to make sure this equality is true. Okay? So again here, this is 3 over 1. This is 5 over 1. So when we multiply these, we just multiply the numerators and the denominators straight through. So 3 times 32 is going to be 96 over 13. I'm adding negative 5 over 13. And I want to see if this equals 7. I'll do red again, because we're still not sure. So 96 plus negative 5, that's going to be 91 over 13. Does that equal 7? Well, if you don't have a calculator, just check, like 13 times 7, does that equal 91? Yes, it sure does. So this whole thing reduces to 7, this left-hand side. So we have that it does equal. So we know our x and y satisfy the first equation. So let's go ahead and check the second equation quickly. 2x minus y equals 5. This is the second equation. So we're going to plug in x and y, 2 times 32 over 13, minus just 1 times negative 1/13. And we're verifying to see if this equals 5. So multiplying straight through on the top and the bottom, 2 times 32 is 64 over 13. Minus a negative gives me plus 1 over 13. We want to verify that this is in fact 5. 65 over 13. Does it equal 5? It does, because 13 times 5 is 65. We can double check that. Quick math. 15, carry the 1, 65, yes. So then 5 equals 5. So this solution should be correct. It satisfies both of our equations. Then our solution works. Alright, now I want to do an example of a system that will have no solution, just so you guys see what that looks like when you end up at the end of the problem, basically. So again, we will first solve, or that's not really what I want to say. First, we want to solve the first equation. Solve first equation for y, because that looks like the easiest variables to solve for. So 2x minus y equals 1 we can, why don't I add the y to both sides? Cancels on this side. 2x equals 1 plus y, and then I can just subtract the 1. So 2x minus 1 equals y. I'm going a little bit faster on this one since we've seen an example of how to do this already. And then next we will plug in y equals 2x minus 1 into second equation. So second equation is 4x minus 2y equals 3 minus 2y equals 3. So I'm plugging in, instead of y, I'm plugging in 2x minus 1. So 4x minus 2 times 2x minus 1. We're verifying, or sorry, we're not verifying. We're setting this equal to 3. So 4x, we're going to distribute that minus 2. Make sure you bring the negative sign with you. This becomes minus 4x, and then minus and minus makes plus 2. And then when we go to combine our like terms, the 4x and the 4x, we have 4x and we have minus 4x, so those are going to cancel with each other, and we end up with 2 equals 3. Well, this is just not true at all. It's never true. There's no value of x that I can use to make this true. So that means there is no solution. So if you end up with some statement like this, where this can never be true, then you'll have no solution. We don't usually say solutions, just no solution. Alright. So now moving on to the second method to solve our systems of equations, we have the method of elimination. So let me quickly go back to the original system, this ax plus by equals c, dx plus ey equals f, and explain how that works. So elimination, the idea is to multiply either one of the equations or both of the equations by some constant. So multiply through by a whole number on both of them or just one of them to get the coefficients of one of your variables to match. And match except for one is positive, one is negative. So here, like, I'll edit this real quick. If I multiply this whole equation by d, so they all get a factor of d, and then the second one by negative a, perhaps, then you can see that these coefficients now match. So if I add these equations together, this variable will cancel out. So that is the idea of elimination. Let's go through the steps on how that will work. So step 1, determine which variable is easiest to eliminate. So again, like, look at your coefficients and see, like, oh, I'll only need to multiply by one equation by one number here. And then figure out which one will be the easiest to eliminate. Step 2, multiply all terms of one or both equations to obtain matching coefficients, like we saw. And you're going to want one of them to be positive, one of them to be negative. We're going to then add equations to eliminate one of the variables, and then solve for the remaining variable. So like in my example on the first page, we were adding those equations to get rid of the x variable, and then we would solve for the y variable. And then again, we're going to back substitute to solve for the other variable once we've solved for one. And finally, we'll check our work. So it seems a little confusing, but it does work better than substitution in some cases when it's not easy to solve for one of the variables. So we'll go ahead and look at an example. So let's now take a look at this example, and we will use the method of elimination to solve this. So we'll want to find all possible solutions to our system of equations. We have 2x minus 3y equals 3 and 6x plus 5y equals 13. So let's go ahead and look at our steps for elimination. We're first going to want to determine which variable is easiest to eliminate. And so, looking at this system, notice that your x coefficients, the second one is a multiple of the first one. So that means I'm only going to need to multiply the first equation in order to get these coefficients to match up. So here the x ones are going to be easier. If we looked at the y's, this 5 is not a multiple of 3, so we'd have to multiply both equations to get to the, it's like a least common denominator, but in this case just the least common multiple. So we're going to want to eliminate the x variable. And that was step 1. So step 2, multiply all the terms of one or both equations to obtain matching coefficients. So I need this 2 on the x in the first equation to become a negative 6. So need 2x to become negative 6x. So that means that I need to multiply the entire first equation, by negative 3. Because if I multiply this 2x by a negative 3, I will get to negative 6x, which is what I want. So let's see, do I do that in step 2? Yeah, multiply. So let's go ahead and multiply the whole equation, the first equation, by negative 3. So you're basically just distributing this minus 3 to every term. So this is going to become negative 6x plus 9y equals negative 9. So this is a new equation that I've created. So step 3, we're going to add equations to eliminate the one variable that we chose. And then we're going to solve for the remaining variable. So take your new equation. I have negative 6x plus 9y equals negative 9. And then copy the second equation. We didn't touch this yet. So 6x, was it plus 5y equals 13? Plus 5y equals 13. And we're now going to add these equations together. So the whole things, and they line up like this, so we're just going to add term by term. So negative 6x and 6x, those are going to cancel out, which is what we wanted. That was our whole plan to begin with. 9y plus 5y gives us 14y. And then 13 plus negative 9, that is going to give me 4. Positive 4. Okay, so we're almost there. We just need to solve this equation for y now. So the last thing to do will be divide by 14. So we're going to end up with y equals 4 over 14. We can reduce this one step. These both have a factor of 2 in them, so 2 over 7, dividing both the top and the bottom by 2. So that was step 3. We solved for our remaining variable, which was y. Step 4, we're going to want to back substitute to solve for the other variable. So step 4, we can take either of our original equations. Let's look at our number here, 2/7. So we'll probably just take the first equation because the coefficients are a little bit smaller. We won't have to do large multiplication. So we'll take the first equation. You can do either. Once again, it doesn't matter, but just to save some time on multiplication, we'll take the first equation and plug in y. So that was 2x minus 3y equals 3. Y happens to be 2/7, so we'll plug that in. 2x minus 3 times 2/7 equals 3. Remember, this is 3 over 1. We're going to want to multiply this fraction times the 3, so 2x minus 3 times 2, 6 over 7 equals 3. Let's take that to a new page. 2x minus 6 over 7 equals 3. All right. We're going to want to solve for x still, so we have to add this 6 over 7 to the other side. 2x equals 3 plus 6 over 7, which is actually just 3 and 6/7 if you want to write it as a mixed number. But since we have to divide by this 2, we need to make this into an improper fraction. So let's do a quick side calculation. 3 and 6/7 is going to become what as an improper fraction? I need to do 7 times 3 equals 21, and then plus 6 will give me 27. 27. So then this mixed number is actually 27 over 7. So coming back over here, 2x equals 27 over 7. Because we're dealing with fractions, we normally divide by 2 here, divide both sides, but I'm going to actually multiply by 1/2, because remember you can, this is 2 over 1, so you can multiply by the reciprocal to cancel out that, that coefficient there. So we'll multiply both sides by 1/2. It cancels on this side. And then we'll end up with x equals 27 over 7 times 2 is 14. So that's what our solution is going to look like. X equals 27 over 14 and y equals 2 over 7. Assuming we did everything correctly, but we'll go back and check our work to make sure we did it right. Let's just go ahead and do that right now. Check. Step 5. Go back and copy my equations one more time. 2x minus 3y equals 3. And then 6x plus 5y equals 13. And my solution was x equals 27 over 14. And y equals 2/7. So remember how we reduce this. Typically, you'll want to write your answers in like simplest form, so you'll want to reduce. But when you're checking your work, it might be easier to leave it as 4 over 14, leave it in unsimplified form, and that's only because you'll notice that x and y already have the same denominator, and we're going to be adding terms. So just to, like, thinking ahead, you may want to use this value of y. So we'll go ahead and try the first equation. 2 times x is 27 over 14 minus 3 times 4 over 14. We want to verify that that equals 3. So instead of reducing again, I'll just multiply straight through. The numerators get multiplied. 2 times 27, that should be 54 over 14. Minus 3 times 4, that's 12 over 14. Does this equal 3? 54 minus 12, that's going to give me 42 over 14. Again, does it equal 3? Well, I believe it does. 14 times 3, doing a quick check, does equal 42. So this equals 3. And the solution works in the first equation. Let's go ahead and verify in the second equation. 6x plus 5y equals 13. Was it 5y? Yeah, 5y. And once again, x equals 27 over 14. And then y equals 4 over 14. So we'll plug in 6 times 27 over 14 plus 5 times 4 over 14 and we want to check and see if this equals 13. Question mark. So 6 times 27, you know, we're allowed to have a calculator on the exam. I think I'm going to go ahead and use my calculator just in case. 27 times 6 is 162 over 14. Plus 5 times 4, that's 20 over 14. Does this in fact equal 13? We need to verify. So 162 plus 20, that's going to give me 182 over 14. Does it equal 13? I'll plug this into the calculator as well. Does 182 divided by 14 equal 13? Well, it does. So that means we did our work correctly. So our solution, which I should have written on the other slide, maybe I did, we'll write it as x equals 27 over 14, y equals 4 over 14, or as the ordered pair. You could also write 27 over 14, comma 4 over 14. Just make sure you get the order correct though, because it does matter. X and y, like this would be x, this would be y. So it's not the same thing if you switch them around. So make sure you get that correct. All right, and then the last thing that we'll do today is do a quick example of what it looks like to have a system with infinitely many solutions. So first thing to notice actually is you can kind of tell something's strange about these equations maybe. You can actually notice that the second equation is a multiple of the first equation. So we're going to run into trouble when we do our elimination. So let's go ahead and do that first. Let's say we want to eliminate the x variable again, because why not? So eliminate x. So that means I need to figure out what I need to multiply by. Multiply 2x by to get to negative 4x, because I want these coefficients to match and be opposite sign. So I need to multiply the whole equation by negative 2, it looks like. And that'll be the first equation. So we'll go ahead and do that. We'll multiply the whole first equation by negative 2. 2x plus 4y equals 3. Distribute that negative 2, that'll be negative 4x minus 8y equals negative 6. So that will be my new equation that I'm working with, negative 4x minus 8y equals negative 6. And we'll add that to the second equation, 4x plus 8y equals 6. Negative 4x and 4x cancel out, negative 8y and 8y cancel out, negative 6 and 6 cancel out. So I end up with 0 equals 0. And so this is always true. So there are infinitely many solutions. So yeah, the thing to keep in mind with those special cases is if you end up with a statement that is always true, then you'll have infinitely many solutions. Like we saw in the other example, if you end up with a statement that can never be true, then you'll have no solution. Otherwise, you'll just have a single solution for these linear systems of equations. All right, and that is where I'll leave it today. Thanks so much for watching, guys. I will see you in office hours, hopefully, or on the day of the final. All right, thanks.